Hi guys, Miss Francis here to talk about population growth. So we have information thus far on how to predict population size, but what if I want to know how fast or slow that population is growing or how fast or slow that population is decreasing? So to understand how much a population's growth might be changing, I need to take into consideration birth and death rates. So scientists have actually created a mathematical expression to explain this relationship where delta n, that's what this triangle means, which is the change in n, is equal to the change in t. So n represents the population size and t represents time. B is the birth rate and D is the death rate. And if you'll notice, this equation actually appears on your AP Bio reference table. So let me ask you this question. If B is equal to D, then there's zero population growth. But if B is greater than D, then there is population growth. If B is less than if B is less than D, then the population size is decreasing. If B is drastically larger than D, if the birth rates are drastically larger than the death rates, and a population is under ideal conditions, that's why the birth rate is much higher than the death rate. For example, there's unlimited resources. There are a lack of limiting factors. Well, then population can grow rapidly. So rapidly that we refer to this type of growth as exponential. And we can actually calculate this exponential growth rate for the population, and it is represented by this lowercase r. Again, the equation can be found on the AP Bio reference table, and it's D, which is the same as that triangle, delta n, or the change in population size, divided by dt, or delta t, also represented by the triangle, change in time, is equal to R max, that is the rate, what we're looking for, times n, where n is that original population size. So if we were to graph exponential growth, such as the type of growth that's seen in these petri dishes down here, this bacteria is growing exponentially in this example, you'll note that on a graph, exponential growth takes the shape of a J, where the growth rate of the population increases as time goes on. So now we're going to take a look at a practice problem. So here's our practice problem. In a population of 100 rabbits, if 10 rabbits are born but no rabbits die, what is the value of R? So in this case, we're looking for the rate of growth. So when calculating the rate of growth, we can use this equation. And I'm just going to rewrite it in a format that makes more sense to me. So delta n over delta t is equal to R max times n, where delta n is the change in population, delta t is the change in time, which in this case is equal to 1 because we're changing by 1 each increment. And this is just an arbitrary increment of time. It might be 1 minute, 1 hour, 1 day, 1 month. N is the population size. So what we're looking for here is to find the change in population growth. In other words, by how much did my population increase or decrease? So let's solve this equation. So delta n is the change in population, which is represented by the birth rate minus the death rate. Our change in time is 1. we're looking for R, that's what we're solving for. And sometimes you'll see it written as R max, sometimes you'll see it written as just R. And our population size is 100, right? That's our N value. So if 10 rabbits are born and 0 rabbits die, that gives us 10 over 1 is equal to R over 100. So if I'm solving for R, I need to divide both sides by 100. So 10 divided by 100 is 0.1. So 0.1 is our R value. It's our rate of change. But if I want to actually find out by how many my population either increased or decreased, I need to multiply the rate by which that population changes by the original population. So in this case, I'm adding 10 rabbits for each increment, or for this first increment of time. So that means that after one arbitrary amount of time, let's say 1 minute, I would go from having 100 rabbits to 110 rabbits. Well, now I want to calculate the population change from 1 to 2. So again, I would take 0.1, but now I have to multiply it by my new population number, by 110. And now I've added 11 more rabbits. So in order to find out my population for that next time increment, I have to add 11 to it. If I want to find out once again how many rabbits are added to that next time increment, I'm going to multiply the rate by which the population increases times the total population. So I'm increasing the population by 12, so I would add 12 to 121 and I would get 133. So if my rate of growth is a positive number, my total population size as I move on in time, not moving down in time, and this arrow is probably confusing, but as you advance in time, as I get further along in time, if my R value is positive, that means that over time, my population size is going to increase. If my R value is negative, then my population size is going to decrease over time. There are 2 types of growth. We just looked at one type, exponential growth, where unlimited resources are available or there is a lack of limiting factors, where on a graph, exponential growth would be represented by a J, where the growth rate increases as time goes on. For example, those bacteria that were growing in a petri dish. But typically, unlimited resources are rare. Therefore, population growth is regulated by what's called a carrying capacity, where carrying capacity is the maximum stable population size that any particular environment can support. And this represents the logistic model of population growth. The researchers actually developed an equation that accounts for this carrying capacity, and it's called the logistic growth equation, where the graph of the logistic growth equation looks more like an S, where you've got this plateau that occurs at the carrying capacity, the max amount of individuals or organisms that can be supported by that environment. So, how well does the logistic model fit the growth of real populations? Well, real populations seem to follow the logistic growth model pretty accurately because our limiting factors are there. We don't have unlimited resources. There is a limited number of food. There is a limited amount of space. There are a limited number of mates. So therefore, real populations follow the logistic growth model. So now if we go back to our rabbit example and incorporate this idea of a carrying capacity, I can use an equation to determine the growth pattern. So think back to our rabbit example. We had a growth rate of 0.1 and our population size was 100. We're going to use that same information in order to calculate logistic growth. So in this case, logistic growth is delta N over delta T, but it takes into account the carrying capacity, which is represented by this capital letter K. And what I did was I just separated this part of the equation into two pieces. So this is my first piece, my first calculation, and then this is going to be my second calculation, where now I add or multiply or divide, whatever the case may be, all of my information. So the first step is to include or incorporate the carrying capacity. So let's do that first. So my carrying capacity, I'm going to assume, I'm just making this number up. 150 is not the actual number for every single organism's carrying capacity. But if I did 150 minus 100 divided by 150, what I end up with is 0.33. And that is this value, 0.33. Now I can plug in my R value. So I can plug in 0.1 times 100 times 0.33. And in this case, that's equal to 3.33. That's how many rabbits I'm adding to the population during this arbitrary amount of time. So now I'm going to add 3.33. I'm going to round it to 3 to 100 to get 103. And now that's my population size. So once again, if I take 150, 150 minus now 103, because that's my new population size, divided by 150, and I end up with 0.31, which gives me, again, some answer that I'm going to round to 3. So now I'm going to add another 3 rabbits for my next time period. Then it would be 150 minus 106 over 150, and it comes out to 0.29. And then when I plug and chug into this section of the equation again, I still get a number that rounds to 3. But over time, you'll eventually notice that the number of rabbits that I'm adding to this population, when that population grows logistically, is actually going to decrease over time. So I'm going to add 3, add 3, add 3, add 3, then I might add only 2, add 2, add 2, add 2, and then I might only add 1 until eventually my birth rates and my death rates are equal and I'm not adding any more rabbits to the population. Here are some practice questions to help you identify whether or not you understand the difference between an exponentially growing population or a logistically growing population.